we have a situation where two balls depicted here on two ramps roll down their respective ramps. And we're given the information that if the first ball rolls all the way down its ramp from rest, it'll achieve an average velocity of 14 centimeter d per cycle. If the second ball runs down its ramp all the way, and that's not what's depicted here, but if it was to run down the ramp all the way, it would have an average velocity of 6 centimeter d per cycle. And of course, if we roll the ball down and time it, it's very easy to calculate these two average velocities. Just divide whatever the length of the ramp is in centimeters d by the number of cycles it takes to get there. So this information will be very easy to obtain. Now, we want to know if you start the two balls simultaneously, and at the instant this ball reaches the end, this ball is somewhere in between. The question is then, where is that going to be? In other words, where is this ball going to be if they're started at the same time? Where is this ball going to be when this ball reaches the end? And how fast is it going to be moving? So I've got a delta S vector here, so I got delta S question mark. I've got a vector that I've labeled V here, and I hope you can read that because I had to squeeze it in pretty tight. But that's a vector indicating the velocity of this thing. And also, what's the time interval? Okay, so what can we do to get a handle on this situation? Well, let's do what we can obviously do. Let's figure out the time it takes the first ball to get to the end. Okay, and that time, and the other bit of information is that the length of this ramp, and this is pretty unrealistic, it's really short, probably shorter than the diameter of the ball. Well, not that short, but pretty short. So we imagine we have very tiny steel balls running down these ramps, and probably an unrealistic situation, but that's the one we're given, and it really doesn't matter that much. So the distance down the ramp is 2 centimeter d. That's only about that far. Got to be a really small ball. Okay. We find the time of the first ball to the end. That's really easy to find. It's something that if you don't know what else to do, you're going to find. And then you're going to go back and read the problem and see if that helps you get a handle on anything. So we can easily find the time of the first ball to the end, which is going to be 1/7 of a cycle. Now, we could also find the velocity, the average velocity, the final velocity of the second ball. Of course, we could find the final velocity of the first ball. Since we start from rest, doing the averaging and everything, this is going to be 28 centimeter d per cycle. Final velocity, this will be 12 centimeter d per cycle. So we could find that information. Turns out we're not going to really need it, so I didn't write it down here. Okay, so what we have is time it takes the first ball to get to the end. That's going to be important because we want to figure out where this ball is at that time. So we're going to have to figure out how long this ball spends rolling. And it's going to turn out to be 1/7 of a cycle. Now you might ask how we're going to time that with a pendulum, and that's a good question, but let's assume that we can do that. Okay, then what we want to do to figure out how fast this ball is going to be going after 1/7 of a cycle, in other words, in the time this ball takes to get to the end, we'd better know the acceleration on this ramp. And we don't yet know that acceleration. We only know it's the ball's average velocity on the second ramp. So we find the final velocity. Okay, this time it's relevant. Up here on the first ramp, it isn't really relevant, not to the question as posed. We find the final velocity, and of course, if the average velocity is 6 whatevers, and the initial velocity is 0, the final velocity would be 12. And the whatevers are centimeters d per cycle, obviously. So that's going to be the final velocity. The initial velocity being 0, and I'm skipping some steps here. I don't like to do that, but in this case, we're dealing with a more complex situation, so I'm not going to write out every last detail. In any case, we conclude at, okay, I don't want to explain too much. Okay. We've got the final velocity, and that's going to equal the change in velocity. We need to find the delta t. Well, we have the delta t. It's 1/7 of a, we're calculating the acceleration. The delta t all the way to the end is going to be the 1/3 of a cycle. So let me put the subscripts on this. Okay, so delta t2 is the 1/3 of a cycle it takes to reach, for this ball to reach the end of its ramp at an average velocity of 6 centimeters d per second. And we get that very easily by dividing the 2 centimeters d by the 6 centimeter d per cycle. I'm saying seconds sometimes, and I'm kind of used to that, so indulge me that when I say seconds, I mean cycles in this case. So we get delta t2 is 1/3 of a cycle, and that's very easy, again, from delta s and the average velocity. This comes out almost immediately. So here's our final velocity. We start at 0. That's going to be our average velocity. So our delta v on that ramp is going to be 12 centimeters d per second, and we're going to divide that by the time it takes to get all the way to the end of the ramp by 1/3 of a cycle. We get the acceleration, which is 36 centimeters d per cycle squared. Now, we need this in order to determine how fast the ball is going at this point and how far it goes. So after 1/7 of a cycle, and how, again, where it is here and how far it goes here, remember that here is where it is when this ball reaches the end of its ramp. So that's going to take 1/7 of a cycle. So the velocity of the second ball after 1/7 of a cycle is what? Well, 1/7 of a cycle, that's your time interval. We multiply that by the acceleration, and we get approximately 5.1 centimeters d per cycle. Other question, and I'm not even sure this question is on the test, but on the problem that you're seeing, but it could well be, so let's go ahead and calculate it. Okay, what about the delta s of the second ball? Now, this is not the delta s from one end of the ramp to the other, which is not the, in other words, not the delta s we used in this calculation. We're done with this calculation. The only reason we did this calculation was to get the acceleration, which we need to find the velocity, and which we're going to need to find the displacement. Okay, well, actually we don't need it, we just need this velocity. Delta S2, and I need some notation here, so I'm going to introduce a little. I'll do that off screen.